Hello everyone, this is Dr. M. Maivili, Assistant Professor, Department of Engineering Mathematics, KPR Institute of Engineering and Technology. Now we are going to see about what is probability distributions. Probability distribution is nothing but uncertainty distribution making. We are going to see about what are the understanding of probability distributions, which are nothing but probability assigned outcome values, then difference between discrete and continuous random variables, then important distributions. We have five distributions: binomial, Poisson, normal, exponential, and uniform distributions. Then we are going to see about the real life problems. Finally, we are going to see about the visualize, that is we are used the technology in visualization. Next one, what is probability distribution? Probability distribution is nothing but it describes all possible values of a random variable can take and how likely each one is occur. Then random variable. Random variable in mathematically random variable assigns a number to each possible result of a random experiments. It having two types, discrete random variable and continuous random variable. Discrete random variable is nothing but countable and distinct values. Continuous random variable is nothing but any value within the interval. Then what is PMF, PDF and CDF? PDF is describes about continuous probability density across the given values. PMF is assigns probability to discrete outcomes. CDF accumulated probability, which is cumulative distribution function. Measurement of the distributions. Here we used mu, sigma square and sigma. Mu is nothing but mean, that is expected value, where the distributions is centered on the average value. Sigma square is nothing but variance, measures the spread of outcomes around the mean. Sigma is nothing but standard deviation, the typical variation from mean expressed in the same units as the given data. Types of probability distributions. Already we know the discrete types of distributions, discrete and continuous. Discrete is nothing but binomial and Poisson. Continuous distributions are nothing but uniform, exponential and normal. Binomial distributions are fixed number of trials, that is two outcomes, either success or failure. And Poisson distributions are counts events occurring a fixed interval of time or a given space. Continuous distributions, we have uniform distribution. Uniform distributions are every value in a range is equally likely. Exponential is models time between events in a Poisson process. Normal having a bell-shaped curve. In real world applications, we have daily life, e-commerce predicting daily sales. We have in a sales counter, we have in daily sales in the sales counter, which is the one of the example of distributions. And second thing, bank call center. We have to wait in the bank center, right? Which is one of the example of Poisson distribution. Then probability distributions, we know about the binomial, Poisson and uniform distributions with formulas, examples and real world applications. What is binomial distribution? In mathematically, we denoted the binomial random variable as P of x is equal to x, that is n ex p to the power x, q to the power n minus x. Here, q is denoted by 1 minus p and n is denoted by number of datas, and p is probability and q is probability of success and probability of failure. P and q are probability of success and failure. This is the one of the example of binomial distribution. We have 10 components are tested. Probability of defect is 0.1 and our question is what is the probability of exactly two defective components. We used the binomial formula. We have n value is 10, p value is 0.1. What is the value of q here? Q is 1 minus p, so 1 minus 0.1, we get q value is 0.9. So substitute all the values in the given formula. We'll get P of x is equal to 2 is NC2, that is 10C2, 0.1 to the power 2, 0.9 to the power 8. We will get 0.1937. there is approximately of 19.4 percentage of exactly two defective components. And these are the main applications of binomial defective products, that is number of defective items in a product batch. Survey responses, counting yes or no answer across a fixed sample. Repeated experiments, success across a fixed number of experimental trials. For example, tossing a coin, we get either success or failure, which means head or tail. Next one, medical testing. Positive results in a group of patients tested for a condition. Reliability testing. Components pausing or failing, falling under stress conditions. Next one, Poisson distribution. In Poisson distribution denotes events occur independently, and here the lambda is denoted by the average rate. In Poisson distribution, probability formula for Poisson random variable is probability of x is equal to x, which is equal to e to the power minus lambda, lambda power x by x factorial. Here lambda is denoted by average number of events per interval. This is one of the example of the Poisson distribution. Traffic problem. In traffic problem, we have two scenarios. One is waiting in the waiting line, waiting the vehicles in the line, and crossing the vehicles. So average vehicles arriving is called arriving and waiting. These are two conditions about the Poisson distributions. Our problem denoted as average rate is 18 per hour. Our question is, what is the probability of exactly 20 vehicles arriving in 1 hour? So in our formula, Poisson formula is P of x is equal to x is e to the power minus lambda, lambda to the power x by x factorial. Here x value is 20 and lambda value is 18. Substitute those values in the given formula, will get 0.0798, which is 7.98 percentage. These are the important applications of Poisson. One of the application is traffic arrivals, vehicles arriving at a toll booth or intersection per hour. And similarly, telephone calls, machine failures, website requests, and hospital arrivals. These are the important applications of Poisson distribution. Next one, continuous distributions. Continuous is nothing but infinitely many values. That is, measurement can take infinitely many values within the range. And point probability, which is equal to 0. The probability at single exact point is 0. Only intervals carry meaningful probability, which is interval based probability. We have uniform distribution. Uniform distribution is nothing but every value in an interval has equal density and define an interval from A to B. The density function is defined by f of x is equal to 1 by b minus a. X varies from A to B. We have one of the example. A person arrives randomly between 10 to 10:30. Every moment in that window is equally likely. This is the uniform distribution on 0 to 30 minutes. Then exponential distribution. Exponential distribution is nothing but events occur continuously and independently at a constant average rate. Here, f of x is denoted by lambda into e to the power minus lambda x, where x is greater or equal to 0. Lambda is called the rate parameter, average number of events per unit time. And this is the important application of exponential: machine lifetime, customer arrivals, waiting time, network failures, and component reliability. One of the example is machine lifetime. We have a modeling time until a machine falls or require maintenance. And customer arrivals, in an hospital we have a lot of customers, and which is the one of the example of exponential distribution, that is time between successive customer arrivals at a service point. Next one, normal distribution. Normal distribution always like in the bell-shaped curve. Here we are some characteristic about the normal distributions. First characteristic is symmetric. Second one is defined by mu1 lambda, sorry, mu1 sigma. Then mean, median, mode are equal, very common in measurement data. The symmetric means the distribution is perfectly symmetric around the center, and we called mu and sigma as mean and standard deviation. In normal distribution and Z score, we have Z score formula. Z is equal to x minus mu by sigma. X is nothing but the given data, given value. Mu is mean and sigma is standard deviation. These are the important applications of normal distributions: student marks, measurement error, manufacturing dimensions, human height, and sensor measurements. For example, student marks test score across large populations tends to follow a bell-shaped curve, which like we have mark from 0 to 100 means, for example 0 to 100 now we have the criteria 0 to 10, 10 to 20, 20 to 30, up to 90 to 100. We have the criteria. That criteria makes a bell-shaped curve, which is the one of the application of normal distributions. Then conclusion. Conclusion, it says that a mathematical framework of modeling uncertainty and randomness. We have seen about what is binomial, Poisson, uniform, exponential and normal distributions of discrete and both continuous random variables. Selecting the right distribution helps convert the real world applications in mathematical models. Then we used the applications in engineering, manufacturing, healthcare, finance, AI, and data science. Okay, thank you so much for this opportunity.